load cell material. With us, we have Professor Titus from National Physical Laboratory, India. He is the well-known scientist in the field of force, torque, hardness, etc. Sir, we are very thankful to you. You have accepted our request to deliver a talk, which is very important for the laboratories, industries, students, and other counterparts, international counterparts of legal metrology. Because we are also having the load cell, because load cell is the most important part of all the weighing and measuring of all the weighing instruments. Most of the weighing instruments are working on the load cell. So it will be very important, very good knowledge sharing session, which we are going to get today. He has a lot of research experience, research papers, students, PhDs, a lot of experience. I cannot say more about him. He's a well-known scientist in India, not only in India, at international level, who has done a lot of research work, research papers, and R&D. I know him since last more than about 20 years. And it is my fortunate that we have with us today Professor SS Titus up. Sir, kindly allow us to share this video of today to all the participants and all our channels, YouTube, etc., so that the participants can be benefited after that. And your presentation, we will also share your presentation on our website and all our portals, so that the people, the participants, the students, the trainees, or the industries will be benefited from it. Sir, one another request I would like to make to you. I need a format of uncertainty calculation. If you can provide us an Excel sheet as well as a PDF form, how to calculate the uncertainty, which we can share with all the participants at the national and the international level, it will be a very good exercise, very good support, very good help to all the industries, all the laboratories who are working in this field. Because there are many problems. People don't understand what are the factors they have to take, which has to be taken, which can be ignored, and how we can calculate the uncertainty and all in these factors. Because these fields are not very simple. We have to learn. We have to spend the whole life in a particular field to understand or to reach at an understanding level. Thank you very much, sir. Now, I think we have few of the participants. If, sir, we will take the participants at the end of this workshop. I would like to request you to kindly enlighten us with your vast knowledge and experience. Please, sir. Dr. Titus, please, sir. Over to you.
Okay, yeah. Thank you, Dr. Ashutosh Agarwal, for your nice introduction. Yeah, first of all, at the outset, I would like to thank the Legal Metrology Department for giving me this opportunity to share the importance of hardness and how this hardness scale is disseminated. So I would like to also once again thank the organizers and the team who is behind Mr. Ashutosh Agarwal in organizing this webinar to sort of disseminate the knowledge and share our experience in this field with the legal metrology team and the officers, those who are working in this area, and also to the industries. I think there was a slight miscommunication. I think it was a written talk, and I was thinking that Dr. S.K. Jain gave talk some time back. I think you would have covered the force and torque. So I was given the responsibility of sharing the experience that we have developed here in NPL, particularly in the field of hardness, how hardness is measured, and how that particular scale is getting disseminated, and how the NABL accredited lab and legal metrology department and all the other industries are benefited by taking this traceability from NPL and establishing their own reference standard and working standards, particularly measuring the hardness in workpiece, which is very important, particularly for most of the mechanical industries. So today I think I thought I'll be talking about what is hardness, how this hardness scale is established at NPL, and how we are disseminating them, particularly to all the NABL accredited labs and the industries, and how effectively this hardness scale is used, for the manufacturing sector in various industries, mostly, I mean, automobile, chemical industries, mechanical industries. So hardness, anyway, as you all know, it's a very important parameter when you are designing some machine, in terms of, achieving good efficiency and the durability and, the effectiveness. So let me just share my presentation, and I think we can go from that. So can you all see my presentation?
Yes. Now we can see your presentation, sir.
Okay, so it's clear, right? And I hope my voice is also audible to
Yes.
all.
Yes, it is very good.
Okay, fine. So I'll be just covering, what is hardness and how this hardness scale is established at the NMI level, first of all. Then after that, what the NMI is doing in terms of disseminating this particular hardness scale to the calibration laboratories, testing laboratories, and to the even to the industries level, so that they can establish their own reference standards, working standards, and testing machines in order to calculate and measure the hardness of different work pieces that they manufacture at their end. So at NMA level, I'll be just covering how the hardness scale is established. When you are talking about hardness scale, there are different types of hardness scale, and we will not be able to cover all the things. We will cover the majority of the hardness scale which are mostly used in the calibration lab and testing lab and industries. Now, first of all, we need to understand what is hardness before talking about how hardness scale is established. What is hardness? Now, we always talk about hardness in a very subjective way, in the sense, sometimes we say, the for instance, sometimes we say, the sole of the shoes must be very hard, so that the durability will be increased. And sometimes we may say, we have to use soft aluminium, for certain applications. But you see, these are all very subjective terms. See, the hard sole of shoes cannot be harder than a soft aluminium in any case. So there we are using a word, soft aluminium, soft metal, then hard sole. So see, this is very subjective, but we can understand, what we are trying to communicate, though in a subjective way. But we don't have any measured quantity to convey this is the hardness of the sole, or this is the hardness of the rubber we are using, or this is the hardness of the soft metal we are talking about. So it is very important to arrive at a number or a figure to designate a hardness value to each and every component that we are using in our day-to-day life. So what is hardness? In general, it is hardness is how resistance a solid matter is to various kind of permanent shape change when a force is applied. So that is one definition we have. And suppose, see, it is the resistance basically offered by any material for a scratch or for a penetration. Because whenever we design any machine, normally there will be a lot of components we'll be using, particularly so the gear wheels, or anything which is coming in contact with one another, there will be a kind of friction. So when there is a friction, there will be a wear and tear. When there is a wear and tear, then the efficiency and the durability, everything of the performance of the machine will get affected. So in order to optimize such components, we need to maximize the production, and we have to maximize the efficiency. We need to check the hardness of each and every value of the component that is going into the integrated system. So normally we will be talking about the indentation hardness. Indentation hardness is a measure that the resistance of a sample to permanent plastic deformation due to the application of force using a sharp object. So they are primarily used in engineering and metallurgy fields. So this is a kind of definition we are having. So these things are all very commonly available. So you can just, have an idea, what is that we are talking about. Hardness means, from a very general perspective, you can say it is a resistance offered by a material to any scratch when you are trying to scratch it, or when you are the resistance offered by a material when you are trying to poke it with a very sharp object by applying certain force. Now, the hardness test is from this two things. What we are understanding is it comes from a premise of two things. One is how much force we are applying on an object and how long we are applying that force, and what is the kind of deformation that we are causing to the material. So from these parameters we have to arrive at a number which may be able to communicate the hardness of the value internationally. So hardness is not a unit. First of all, we need to understand this very clearly. Like, force, torque, all these pressure, all these things we have a unit. It's a unit. But hardness is not a unit. But hardness is a very important parameter. So how to communicate? So now we are applying certain amount of force using certain type of object, a sharp object. The sharp object will have certain geometry, and that the sharp object is used to apply certain amount of force on that material for certain period, certain duration of time, and what is the kind of deformation that is making, and what is the kind of geometry of the deformation, and what all we can measure from that geometry, and from that geometry we need to arrive at a number, and that number should communicate what is the hardness of the value. And second thing is, when it communicates, that should be internationally acceptable and it should be understandable. So that is the idea behind the hardness. So hardness is an empirical measurement. Though it is empirical, it communicates the requirement of all the industry. It is not a unit. This is first thing you need to understand. Okay. Now, hardness is the result of a measurement performed on a test piece under standard condition. This is what I was just explaining to you, based on agreed convention. So for this, the standards are there. So we have several standards. Okay. So indentation is made under prescribed condition. This is what I was telling. Then determination of a characteristic dimension. There are three things involved in this. So you take a sharp object. Sharp object means not any type of object. The sharpness of the object is very well defined in the standard, and the indentation is made under prescribed condition. So how much time, how you have to make that indentation. Then after making the indentation, there is a deformation on the sample. Then you have to measure certain geometrical thing from that indentation that is made by that object for that particular force, for that duration. Then you are going to use some calculation and you are going to arrive at number. This is a very general principle which is applied internationally, and these things are defined in all these standards. Now largely I think we will be talking about three major scales. One is Rockwell, and another one is Vickers, the other one is Brunel. So these are the three scales we will be talking about. All these three scales are very well written in these standards, IS 1586, ISO, because mostly it's all coming from ISO and ASTM standard, and IS has adopted these standards as it is in most of the cases, and in some cases there may be slight modification. So ISO 6506, it talks about the Brunel hardness scale. ISO 6507 talks about the Vickers scale. ISO 6508, it's all in order, so that is why it's easier for you to remember also. This particular standard talks about the Rockwell hardness scale. And all these three standards are coming in three different parts actually. This has got part 1, part 2 and part 3. And Indian standard has adopted this same ISO standard as it is in most of the cases. And this standard, as I told you, all these standards have three parts, the part 1 and part 2 and part 3. And part 1 always talks about the general principle, how this hardness test has to be performed. Okay, and it talks about what is the kind of indenters one has to use, what is the kind of sharp object one has to use for making this penetration. Then what are the different scales available? So that is what part 1 generally talks about. Then the part 2 of the standard generally talks about the testing machines of the hardness measurement. So there are several testing machines which are used by the calibration laboratories and the industries. How these testing machines have to be calibrated, what is the permissible tolerance what one can have for measuring the hardness. So part 2 generally talks about all the testing machines of the hardness measurements. And part 3, it talks about the calibration machines. It is one step advanced compared to part 2. Part 2 talks about how standard hardness blocks can be calibrated. So what is the requirement for the kind of machine that should be used for calibrating the standard hardness block? Because standard hardness block is going to be a kind of reference material for calibrating all the testing machines across the country. So the calibration machines have certain specifications that is very tight. What is the kind of indenters and what should be the geometry, what should be the tolerance in the geometry, and what should be the force, what should be the tolerance the force, and what type of timing cycle one has to maintain. So all these things are very tightly prescribed in part 3, especially for the calibration machine, and most of the NMIs will have machines which comply to this particular part 3. So that is very, very important. So when we use a part 3 machine, when we have a machine which is comply to the requirement of the part 3 standard, then we can use that machine for calibrating standard hardness blocks. So that block will become a kind of reference material. It becomes a standard material for calibrating several testing machines. So now this is very important. So I have already communicated a message like hardness is not an unit. Hardness is an empirical value which is arrived from the convention of the standard which is written based on this ISO and this IS standards. So it is a procedure which we have to strictly follow, and we have to comply to all the specification and the tolerances which are given in the standard, and we have to establish the machine fulfilling these conditions. Okay, now the scope of our talk will be mainly the direct method for checking certain functions of this machine, how we have to see the machine, whether the machine is really in a position to calibrate the blocks. And also all the machines what are calibrated, they can also be checked by an indirect method. So whenever we are using a method for calibrating the hardness block, we have to check the performance of the machine both directly and also indirectly. For direct measurements, we need to calibrate the forces, we need to calibrate the indenters geometry, and we have to also calibrate the machine for its timing cycle. And for indirect calibration, we can use the reference material. That is, reference material means the standard hardness blocks which are calibrated from an NMI or from the accredited labs. I like this UCAS is there. Even several. Even now in India also we are having several accredited labs which are having standard blocks, and we can take those blocks and we can check indirectly whether the machine is performing, giving the results as per the specification laid down in the standard. Now, so the indirect method may be used independently for periodic routine checking, because if you want to keep always check on your hardness measurement, then you have to keep on checking the machine and its performance. And if a testing machine is used for other methods, it shall be verified independently. Sometimes some hardness machines can be tested for other purpose also. So we have to be very careful whether the indenter's geometry is not deformed by the other methods. So we have to every time we need to check independently whether the machine is performing well or not. Then only we can be sure of what we are measuring using that particular instrument. So it is also applicable to all the portable hardness testing. There are several portable hardness testing machines are also available now. So that for the same condition is available for that also. Now the hardness scale definition. So now I have already told you. So designation of the hardness scale. It is the first is definition, and the hardness reference machine, and the hardness reference blocks. So this is how the dissemination from NPL takes place as far as the hardness scale is concerned. So this is the unbroken chain of traceability of hardness scale. So it's starting from the international definition of hardness, which is accepted by all the countries and all the NMIs with the standard which is written, and that standard, this hardness measurement scale depending upon the national standard of force, because force is a component. I have already mentioned how much force you are applying on a sample, and the national standard of dimension, because after making the indentation you are going to measure either the depth or the diagonal or the diameter depending upon the scale. I mean the deformation that is made on the sample by the indenter, that is particularly the area of the indentation that is made by the sample you are taking. So dimensional component is coming into the hardness measurement. So we need to make sure the dimensional component what you are measuring on the deformation that has happened on the sample should be traceable again to the national standard of dimension and the national standard time. Again, we are applying the force for a particular time. So you have to make sure whatever the time, whether it is 4 seconds, sometimes 15 seconds, 10 to 15 seconds, all these things should be independently traceable to the national standard. If all these three components, because these three factors which are involved in hardness measurement, though it's an empirical number, though it's not an unit, these components, these are all defined units. So these things play a role, and all these three components should be independently traceable to the national standard. Then with these parameters, we are achieving the hardness standardizing machine in Rockwell, Vickers, Brunel. So that once if you achieve all these things independently and if you establish a machine, then that machine we can call as a primary hardness standard. So once the primary hardness standard is established, which is independently traceable, I mean independently the force, dimensional component and the time which are independently traceable to the national standard, then we can call that as a primary hardness machine. And whenever you calibrate any block, any standard test piece, as per the procedure written in the part 3, I have already mentioned to you that every standard has 3 parts. If you calibrate any hardness block as per part 3, then that block can be treated as a reference block. That is treated as a standard reference block. So that is again a standard which is used for calibrating several hardness calibration machines, testing machines, and in all the working machines, everywhere it is used for calibrating the machines. Once all the machines are calibrated, then the whatever because every industry has a different need. Actually, if you take automobile industry, there a lot of gear parts, this wheel rim, and if you take even this watch industries or chemical industries, everywhere there are different components, so they can test the test pieces independently depending upon the requirement and what is the scale it is required for them. Excuse me. Now let us come to the Rockwell hardness scale. Now we have to see how the Rockwell hardness measurement is done. So Rockwell hardness scale has different. There are several scales. We'll come to that. First of all, let us understand what is the principle and know how this scale is established and what are the critical factors involved in this Rockwell hardness measurement and how we have to optimize and what is the requirement from the standard. Okay, so this particular scale, it works in the following ways, I can say. So it uses an indenter. So indenter is a very integral part of any hardness machine, I have already mentioned. So what is the kind of indenter which is used in this particular hardness? In Rockwell hardness, generally a conical indenter is used. So you can see here the indenter is a conical indenter. So either it can be a diamond indenter sometime or it can be a ball indenter. There are two types of indenter, we'll come to that. Okay. So the diamond indenter, the conical angle has to be 120 degrees plus minus 0.1 for the calibration machine. Okay. So I mean we'll come to the geometrical part and the requirements little later. Now at this stage you can just visualize it as a conical indenter is used in the case of Rockwell hardness. How this conical indenter is used to make a penetration. So we need to apply a force. So what is the force which is required to make the indentation on a sample? So this conical indenter is plunged into the sample by applying a force of 10 kg at the initial stage. So apply a force of 10 kg, that we call it as F naught. Okay. Then you make a initial indentation as just a penetration on the sample. then you have to wait. So you have to apply this force as per the timing cycle which is defined in the standard. Okay, so within 1 to 8 seconds you have to apply. Then after that you have to apply some additional test force. Additional test force which is sometimes 50 kg, it is sometimes 90 kg, it is sometimes 140 kg. So if you apply 50 kg, the total force is going to be 60 kg. If you apply 90 kg, the total force is going to be 100 kg. And if you apply 140 kg additional force, is going to be 150 kg. It's already written here. There are, so these three scales will make ABC scales actually with the diamond indenter. You don't have to really worry about the numbers at this stage, because what you have to see is, first of all, you apply a preliminary force. Okay, let me not give you any number. So you have to apply some preliminary force, then you have to wait, then you have to apply the total test force. Okay, so that is the additional test force. Then you have to remove the additional test force. Then you have to measure how much permanent damage or permanent indentation depth this particular conical indenter has made on that sample. So that permanent indentation you have to measure. Yes, most of the times this hardness, Rockwell hardness is used in the metals. So when you put, after removing the additional test force, the material will, again, because of its elastic nature and nature of the material, it will go back to its original state to some extent. But whatever the permanent damage is made on the sample, it will remain as it is. So that measurement is called E. So E is nothing but you measure this indentation, permanent indentation, in terms of micron. Okay, actually you have to convert it into mm. Then you have to take every 2 micron as 1 E scale. So you suppose if you are making 100 micron depth, finally if you are getting 100 micron, then every 2 micron you have to take it as 1 E. So 100 micron will make 50 E basically. So then that 50 you have to subtract from 100 to get the hardness scale. This is how the Rockwell hardness number is obtained as per the standard. So what we are doing here is, we are simply applying a 10 kg of initial force, then we are applying some additional test force as per the requirement of the scale, whether it is A scale or B scale or C scale. All these three scales have different forces. Then you apply that force, then you remove that additional test force, then you measure the permanent indentation depth. So now the dimensional component is coming here. So here we are measuring the depth. So to measure the depth, you have to use either laser interferometer or some other precise mechanism. Sometimes, in the lab they use spiral microscopes, and they use Heidenhain, some other length measuring system to achieve the better accuracy of measuring the depth. So how best you can measure the depth, that is again going to define the accuracy of the machine. Okay. Now, after measuring the E, that is, after measuring the E, you have to subtract it from 100 for certain scales, and if you have to subtract it from 130 for certain scales. Okay, there are different scales. I told you it has got a very large spectrum. So the large spectrum basically comes from the kind of indenters and the kind of forces, different forces you are applying on the sample. So now let us just look at the timing cycle a little bit. Okay. Let me just give you an idea of the scale. Okay, these are the different scales. Okay, we have HRA, HRB, HRC, HRD, HREW. There are a lot of scales like this. Basically, there are 9 common scales you can say. So HRA, we are using a diamond indenter. We are applying a preliminary force of 90, that is 10 kg. Then total force is 60 kg. And in the case of HRB, we are using a ball indenter. Okay, it's a ball indenter. It is having a diameter of 1.5875 mm. That is the ball diameter we are using. And again, the preliminary force is 10 kg. And in this case, the total force is 100 kg force. Okay, but in all these cases, we are measuring only the depth. Okay. In HRC, again, it is a diamond indenter. In HRD, it's a diamond indenter. Whatever I have marked in blue, it is diamond. Whatever I have marked in red, it is the ball indenter. And again, there are other scales, HREW, HRHW, these things. I mean, we have to use a ball indenter of 3.17 mm diameter. So that is the difference. So I mean, you can change the diameter of the ball and you can derive more scales by applying different forces. But the principle is only 10 kg and 10 kg is the preliminary force, and the additional force is either it is 50 kg or 90 kg or 140 kg depending upon the scale. And it has got also superficial scales. I told you in the regular scales you are applying 10 kg force. There are superficial, because there are some materials you will not be able to penetrate much. So there are, I mean, you have to use the superficial scale. In the case of superficial scales, again you can use the diamond indenter, and also you can use the ball indenter of 1.5875 mm diameter. So here the difference is, for a preliminary force you are applying 3 kg force, okay, and for a total force it is 15. HR 15 means 3 kg. The total force is 15 kg with the preliminary force of 3 kg, and it is 30 Newton, that is 3 kg force and additional total force of 30 Newton, okay, 30 kg. And in the HR 45 scale it is 45, okay. Because this is a very small force, then the penetration depth will be small, so there are some metals which are very soft, for that it is used. Similarly, for the ball indenter also we can use ball indenter for the same force, 15 kg, 30 kg and 45 kg, and this scale is also part of the Rockwell scale, and we call these scales as superficial scales, okay. Now this is the timing cycle, I mean, I was talking about. So when you apply the preliminary force, so this is how the preliminary force, you have to maintain the timing limitation that is given in the sample in the standard. Then after waiting for certain time, then you have to apply the total test force. The total test force, this RAM is very important. Again, you have to apply this total test force within 1 to say maybe 4 seconds you have to apply and complete. Then after applying the additional test force, then as per this time chart, you have to wait for some time, that is 4 seconds. Then after waiting for 4 seconds, immediately you are only releasing the additional test force so that you have applied. Then after releasing the additional test force, within certain time you have to make the measurement. I'm sorry, throat is not in good condition today. Okay.
Even
So
I'm sorry. I'm sorry, sir. I understand that you are thought is not good.
Suddenly because
It's
this.
putting a lot of pressure.
Okay, yeah, a lot of pollution. Okay, now this is how the Rockwell hardness scale, or the number, you can say, because I always call it number, because you should not get the feeling that hardness is a unit. Hardness is not a unit. Hardness is a conventional number which is obtained by following strictly the procedure that is given in the standard, and we are arriving at that number. So is there any question, I mean, about this hardness measurement? Just to get some feedback, whether they are able to. Any question or any doubt, or is it clear? Everything is clear?
Sir, we will take the questions at the end of the program.
Okay, fine, okay.
Because
So,
all the participants are now not able to speak now.
Okay, so this is the, I mean, so now what you have to keep in your mind very clearly is, in the Rockwell scale, we are using a conical indenter, okay, which is having an angle of 120 degrees and a curvature of 0.02 mm, and this velocity of the indenter reaching the surface has to be optimized. Holding time of the preliminary force, it has to be optimized as per the standard, and the testing force loading speed, this RAM, this is 1 to 4 seconds, I said, this has to be optimized for a primary machine. And total test for duration time, this time has to be optimized. Then after that, time before reading the permanent indentation depth, then you release the additional test force. Time before reading the permanent indentation depth, there is a time given. Within that time you have to measure quickly. You cannot wait for a long time, then you cannot come back and measure. All these things are very, very important. Why? Because these are all very small things and simple things. But if you are not strictly adherent to all the conditions, then the number will change. Basically, you will get a number because you will not be able to make out whether the hardness what you are mentioning or what you are giving for the material, whether it is same or not. I mean, you will not be able to ensure. Okay. Now I think this is what I have already explained to you. After making the permanent indentation and you are measuring the indentation depth in terms of mm. So I told you, if you are going to get 100 micron depth, then this is this h by n. H is the, you can say, the depth, and this, if you are dividing it by 0.002 mm, you have to convert that. I mean, this is you can convert it into mm or micron, what it is, whichever way you feel is convenient for you. And then you will get a number, say 50. Supporting I am giving an example of 100 micron, so 50. This n in the case of A and C, it is 100. Okay, so if you subtract this 50 from 100, then the value of that hardness of that material is 50 HRA, you can say, or 50 HRC, you can say. But in the case of B, this N is not 100. In the case of B, it is 130. Again, this is an empirical number. It is accepted number because the maximum one can reach in the case of B scale is 130. So that is why it is defined like that. The maximum penetration, and depending upon the material, because the material may be soft relatively, because that much penetration. In the case of Rockwell, why it is kept 100? Because it will be a hard material, and in the diamond cone, if you are using a diamond cone, up to certain level it can go in maximum in all the even the hardest material you can have. So 100 is a kind of number. I mean, they have chosen the standard after making several discussion. Then this 100 is 100 minus 50, it becomes 50 in that case. And here in this case, if it is 100, it is going to be 90 HRB, right? See the difference. So 90 HRB here. So H is the permanent indentation depth, and the scale unit for specific thing is either 0.002, it is for the Rockwell ABC, and there is one more thing I have mentioned here, 0.001. This is for the superficial scale. For superficial scales, we have to divide it by 1 micron. So that is why, because that is still softer material. So this is how the hardness, the entire Rockwell hardness scale is derived. So now we have covered the complete the definition and how the Rockwell hardness measurement is done using a machine which is fulfilling the requirements laid down in part 1 and part 3 for the standard hardness block, and the requirement that is given in part 2 for the testing machines, basically. Okay, so these are the Rockwell hardness scales. Once if you get the picture of the Rockwell hardness, then rest of the things, for Brunel and Vickers, it is much easier, because its only thing is you will have different type of indenter and you will have different type of forces. The process is that the procedure is the same. The standard is different, the procedure is the same, and what you are going to measure in those scales, it is different. That's all. Because we need to have a large number of scales, because we are using variety of materials from rubber to steel and diamond, everything is there. Since we have a vast type of different type of materials in the universe, so different materials have different hardness scales, and people have to, after a lot of research or after a lot of optimization, what is the best hardness value they require for building a machine or building a certain component, that they have to decide, and accordingly they will have to ask for the hardness value. Now this is just a picture of a machine. It's a very simple machine. So you can see this is the indenter part. So you can see these are all the standard indenter, which is having a diamond tip. And after making an indentation, the indentation will be like this. You can it's just an image you can see. And these are all the weights, different weights which are selected or used for applying the required forces. This is one type of machine, which will give you the uncertainty of 0.3 HR in the ACD scales and 0.5 HR in the other B, E, F, G scales. Okay. So this is one rock. This is the indenter, and for a ball indenter, I mean you have to use the ball appropriately. Either it is 1.5 mm ball or 3 point something ball. You can, that is depending upon the scale. Now let us come to the Vickers hardness. Vickers hardness scale is also equally important. This hardness measurement. Vickers hardness is also used for several applications by the automobile and all the other industries. So here also the indenter, again, every now you are very much conversant. For an hardness measurement, you need an indenter. You have to apply certain force and you have to maintain it for certain duration, and you need to have a proper measuring system for measuring the indentation that is made. So here again we are using a diamond indenter, and it is a pyramid type indenter. So it has got an angle at the vertex of 136 degrees. I mean, again, the tolerance here should be plus minus 0.1 for the primary hardness, primary Vickers hardness machine. Okay. Now, when you use this kind of indenter, pyramid indenter, you will get an indentation of a kind of rhombus shaped indentation it will make. So in Vickers, what we normally measure is the diagonals. So you need to measure the diagonals that is made by this indentation, and for measuring the diagonals you need to have a very precise microscope which is calibrated again by your dimension metrology department. Now how this hardness value is again obtained for HV value. So we have because normally you can in a general way you can say this hardness is directly proportional to the area of the indentation that is made by the indenter. So in a way, so it's a geometrical thing. So it is proportional to this particular area. So it is the hardness, the HV, because hardness is equal to constant. This is again given in the standard. Constant multiplied by 2 times force sine theta by 2 divided by d square. So F is the force, how much force we are applying, and theta is that 136 degree, that that pyramid type conical pyramid type indenter that we are using, and d is the diagonal length that you are measuring using the microscope. So d, you have to measure 2 d's. I mean then you have to take the average and you have to use that d for establishing the Vickers hardness. So this constant is nothing but 1 by g, that is the gravity force, and then you will get this is 0.1. This is a simplified form you can say, because this 136 degree is not going to change. So the Vickers hardness is equal to 0.189 into F by d square. So this is the conventional formula which you have to use as per the standard for getting the Vickers hardness of a particular material. So now again the thing is the same. It is repeating. What are the different type of Vickers hardness available? So HV5, HV10, and we have micro Vickers. Sometimes we go in terms of 10 grams, 20 grams, 50 grams, 100 grams, like that. We have the lower scale also. So this HV5, it means we are applying a force of 5 kg. Here there is no concept of preliminary force and total test force. Here we have to apply the total 5 kg force on that sample using the pyramid indenter. Then we have to release that force. But how much time? Here there is a tolerance of 10 to 15 seconds. I mean the standard is giving. So you have to define how much time you are applying that standard force on the sample using that pyramid indenter. Then you release that force. Then you can put the sample under a high precise microscope and you can measure the diagonal. So we have HV5 scale, HV10 scale, up to HV100 scale. So depending upon the requirement, you can use this scale. And micro Vickers, these things we can call as micro Vickers scale, 0.2, 0.3, again it is 200 gram, 300 gram, 500 gram. These are all, even 0.01 is also there. So these are all micro Vickers scales you can say. Okay. So HV scale is again it is very vast, and of course for the micro Vickers scale, only thing is the tolerance in the pyramid cone is different. So it is slightly because the tip again it is 136 degrees, but the conjunction length and other things, there is a limit which the indenter has to satisfy. Okay, yeah. So So this is the okay. So this is the hardness standard machine, HV machines we are having here in NPL. So this is having a scale of HV1, HV2, all these scales. And naturally in the higher scales, if you are applying a larger force, then the indentation, diagonal, everything will be very large. So you can make a good measurement. So the uncertainty in the HV50 and above is 1%, and in the lower scale, because of the uncertainty in the dimension measurements and the angle, everything, it is very high. So the best uncertainty what you can get in the micrometer scale is 1.5%, right? So this, I mean, this machine is also having some Rockwell scales, that is, it is mentioned here, and these are some of the salient features of this particular scale. It is fully automatic for making the indentation as per the specification of the ISO standard. Force application is through dead weights with the load cell to monitor. So whenever you apply the force, I mean, the force has to be properly monitored, whether you are applying the required force as per the standard. There shouldn't be any variation, and it should be within the limits. And the microscope and the interferometer method, whatever you are using for measuring the depth or for the diagonal, it has to be calibrated. So this particular machine is having a laser interferometer, because this is also having a Rockwell scale. So for Rockwell scale, we need to measure the depth, so we use a laser interferometer in this case. And for the Vickers scale, we have to use the microscope with CCD camera and with the resolution of this 50x and 0.01 magnification of 50x and resolution of 0.01 micron. Okay. And I mean, this particular machine we used even for the intercomparison in the Rockwell scale, and this kind of machine is used in several NMIs. Actually, it's not only in India, like in Dream, Italy, and in Metro, Brazil, and Metas in Switzerland. Okay. Okay. Now let us get the feel of this Brunel hardness. So now, I mean, now you are very much conversant with the hardness scale, how it is established. You know it has to have an indenter, it has to have some application of force, then it has to have a proper dimension measurement system for measuring the indentations made by the indenter on the sample. So in the case of Brunel, it is the same thing. Again, we need an indenter, and we need a measuring system, and we need some mechanism to apply the force. So here we are using mostly ball indenter. So the ball indenter is having either 10 mm diameter or 5 mm diameter, 2.5 mm or 1 mm. There are different diameter balls you use, and again the force applied here is pretty high actually. The Brunel hardness. The Brunel hardness, we apply force from 1 kg to 30 kg force, 300 kg force we apply. So here is the scale, you can say. So it is 10 by 3000. It is 3000. This is 10 means it is this is the diameter of the ball which we use, and we apply a force of 3000 kg. So you'll get this much force on the sample. So either it is 3000 or 1500 or 1000 or 500, 250. So this will give you the spread of the large scale. So by using 10 mm ball, by applying this much force, you can have 6 different scales. Now you change the ball to 5 mm and you change the force, right? So it is starting from 1 mm ball with 1 kg force to 3000 kg force. You can have the entire spectrum of the Brunel hardness scale. Now, what are you going to get here in this case? In the case of Rockwell, you measure the penetration depth. Okay. In the case of Vickers, because of the pyramid indenter, you got a rhombus shaped indentation. You measure the diagonal. In the case of Brunel, you are going to get a circular indentation. So you have to measure the diagonal length at 2 different places. Then you have to take the average and you have to arrive at the number. So that will give you the Brunel hardness value. So this is again, so now you have got the large number of hardness scales. In Rockwell, you have A, B, C, D, E, F, all these scales you are having. In the Vickers, also you are having HV1 to HV100, and the micro Vickers scale also you are having 0.01, 0.02. There are different forces and different spectrum of hardness you are having. In the Brunel also again, 1 kg to 3000 kg you are applying force, and you have got a large spectrum of hardness scale. So depending upon the requirement, what scale one has to have, what is the hardness value for a particular application, after making the correct choice, one can ask for one can ask and specify this is the hardness value I require for developing this kind of system or this kind of a machine. Now, again, this is the mineral hardness machine. We have at NPL, we have two different machines for achieving the entire scale, because 1 to 3000 kg we can have it in a single machine. So we have two machines. It's from 1 kg to 62.5 kg. We have one machine. Then from 62.5 kg to say 3000 kg, we have another machine. So, but if you look at it practically, even the entire scale is not used by all the industries. So majority of the industries require 10 by 3000, or some of them require by 10 by 1000, and then 2.5 by 187.5 scale is largely used. And the Vickers, of course, there are people use HV1, HV30, and micro Vickers scale they use, and Rockwell A, B, C are very largely used. These are the scales very widely used, though we have a large spectrum of hardness scales. Okay, now how to verify these machines? This is very, very important now. Actually, now we just saw now how the hardness scale is achieved, how hardness measurement is done, what are the type of requirements. Now you are very much clear. Now you need an indenter, you need an application of force, and you need to measure the indentation depth, or the diagonal, or the diameter that is made by the sample, I mean the indenter. Now, how to verify all these system that we have established to generate or to establish these scales, these hardness scales? So it involves, as again, this is also very well defined in the standard, how the machine has to be verified. Because some of you may be calibrating your machines at your end. So it requires the direct verification and the indirect verification. There are two methods which I slightly mentioned in the beginning itself. So direct verification or indirect verification, both these things have to be done at a regular interval. And if your machine is used more frequently and in a more rugged way, then you have to check the hardness value of the machine or the performance of the machine using standard blocks every now and then as per your use. Okay. Now the direct verification has to be carried at regular interval, and it involves the calibration of any machine involves the calibration of the test force, because force is a component which you already see. And the second thing is verification of the indenter. The indenter geometry has to be verified, and the calibration of the measuring device, and the verification of the testing cycle. These are the four components which involve in establishing the hardness machine and disseminating the hardness scale. Now, how to make now? So, for the testing of the forces, what is the requirement? For testing of the forces, we can use even the class 1 in instrument, which is calibrated as per ISO or IS 4169 standard. So 0.00 class or no 0.5 class, it's not class 1, it is 0.05 class or class 00. These are the load cells, or the load cells you can use for calibrating the forces, because the force requirement is F plus minus 0.1%. So it is not I mean, you can even use load cell based hardness machine, which are very common nowadays. In NPL, we established hardness machine with dead weight application of forces. In managing the dead weight machine is much more difficult than load cell based machines. So load cell based machines are very simple machines. Nowadays several load cell based machines are coming, which are good enough, because the force uncertainty is not that stringent in the case of hardness measurement, because the dimensional part and the indenter part is it's very critical. So you can use load cell based machines instead of even dead weight machines, and this force verification has to be done using load cells. And this force verification has to be done at different levels also. I mean, normally when as we calibrate these UTMs and the other machines, we have to follow the same procedure, somewhat similar to that, but it is not exactly as per 1828. you have to put the load cell, and you have to measure the force, I mean rotating the load cells at three different positions. And also, because sometimes the block height, the block thickness are all different, so you can measure the force even at three different heights also. So that will give you a very good idea whether the machine is applying the required force as specified in the standard with the tolerance mentioned in the standard. So that we have to ensure by calibrating the force independently. Okay. Three force measurements shall be made at each test force at each position of the plunger. So this I have already mentioned. So you have to rotate it, and you have to take at three different heights depending upon because of the thickness of the sample. Sometimes it varies. So all these this particular factor you have to take into account when you are calibrating the machine for the force parameter, calibrating the hardness machine for the force component. Now the indenter part is there. Actually, for the Brunel indenter, actually the ball size, actually it can be plus minus 1. It is for the testing machines normally, and whatever I have mentioned in the within the bracket, it is for the calibration machines for the standard blocks. So this is the same thing for the Vickers and for the Rockwell also. So Vickers, I mean, if the force application, because normally we talk about micro Vickers and the normal one. So micro Vickers means when the force is less than certain value, that is 1.96 to Newton, and then the application of the force can be plus minus 0.1 in the case of testing machine, and in the case of calibration machine it's plus minus 0.1%. And if the application of force is less than that, actually I mean for the micro Vickers, then the tolerance is little higher actually, because small forces, definitely the uncertainty will be definitely high. So it is 1.5 for the testing machine. Again, for if you are talking about the calibration machine, it has to be very strict. It has to be 0.5%. And then if your machine is not satisfying any of these things, so in the case of Rockwell also it is mentioned, if the machine is not satisfying any of these requirements, then it cannot be used as a calibration machine or testing machine. That you have to be very clear about it. And in the case of Rockwell, the application of preliminary force, it can be plus minus 0.2 and 0.02 for the calibration machine, and the total test force is 1 and 0.1%. Now the verification of indenters, actually, I have already mentioned, I mean in the Rockwell scale we are using a conical type indenter. So in the conical type indenter, I mean the cone angle is 120 degrees, and it has to be plus minus 0.1, and the radius of curvature of the tube measured shall be 0.2 plus minus 0.005 mm. So this is the specification which is given. I mean these are all well written in the standard. And the thing is, I mean whatever indenter or whatever the force we are applying in the machine, it has to fulfill these requirements. So in the case of Vickers, again I told you, I mean we are using a pyramid shape indenter, and this has to be calibrated. I mean all these indenters have to be separately calibrated for its dimensional parameter. Okay, and it is 136 and plus minus 0.1, and the angle between the axis of diamond cone and the axis of the folder, I mean it shouldn't be more than 0.5 degrees in the case of testing machine indenters, and in the case of calibration machines it should be 0.3. Now I mean these numbers actually they are all very very critical. I mean we may not be able to really understand, appreciate how difficult or easy to make an indenter with this particular specification. Particularly if you want to establish a calibration machine, getting an indenter is not that easy. That is why even I mean though you are able to establish a machine for the force component, and even if you have a measuring system, the indenter is the biggest challenge for part 3 machine. What happens is, when you want to after not many suppliers are there even all over the world for the indenter for the part 3 machine. So once you, even after making the indenter, And if it is not fulfilling this stringent requirement, then it becomes a kind of waste. So you make a diamond indenter. So if you make say 100 indenters, maybe one or two will qualify for the part 3 indenters. So for part 3 indenters, part 3 means the machine which is used as a calibration machine for the standard hardness block. The indenter is a very critical component. So I think some of you, maybe the industrialists who are sitting here and listening, then you can just take up this challenge. Then you can see how we can make and produce the indenters for the part 3 machine. So you can get the required specifications and the exact dimension that is required standard, which is written in part 3 very clearly. And then you can also get the input from some of the manufacturers who are manufacturing this indenters. Then how best we can make our own indenters in our country. Then we can try that actually, since I mean many industrialists and this legal metrology team is here, so I thought I can throw up this challenge to them. Yeah. Okay, so I mean, otherwise, the rest of the things is very simple. So only thing is you have to strictly follow the procedure what is given in the standard. So the weakest hardness standard, again the indenter part is there, and every range, the force. I mean, we already saw. I mean, it is starting from 1 kg to 100 kg. It is there. Then below 1 kg also 0.01 gram is also there. I mean, so that covers the entire range. So what is the tolerance again in the force? So that is what is given here in this table, and you can see it. So one is for the testing machine, the other one is for the calibration machine. So calibration machine is always it has to fulfill a little stringent requirement. So similarly for the Brinell indenters, the ball indenter used in Brinell hardness machine are highly polished and free from defects. And these are all important factors actually, because ball indenter means, I mean, we cannot use any type of ball. It also has to satisfy all the requirements, how polished it should be defect free, and what should be the curvature, and all these things are mentioned in this standard. So I have given you the value here in number. So if it is a 10 mm diameter ball, then the tolerance, it should be plus minus 0.005 mm. That is for the testing machines indenters, and this is for the calibration machine indenters. So it has to satisfy all these requirements. So calibration of the measuring device again. So I told you it has to be calibrated for the force, it has to be calibrated for the indenter. That now it has to be calibrated for the measuring device. The hardness machine has to be calibrated for its measuring device. So for Rockwell scale, the depth measuring system has to be calibrated not less than 3 intervals, including intervals corresponding to the lowest and the highest hardness value. Okay, now we may not use the machine in the entire range, but whenever we calibrate the measuring system has to be calibrated for the entire range. So whatever the maximum penetration depth it can make, I mean, if it is 20, if you are talking about 20 HRC, then the penetration depth is about 80 micron, and if you are talking about 60, then it's going to be 120. So I mean, so you have to calibrate the measuring system for the entire range. I mean, it should be within plus minus 0.005 for this, and plus minus 0.001 mm accuracy should be there. So this is again is an important thing to achieve the required accuracy, and whether it is a testing machine or the calibration machine. Similarly, for the Vickers, the measuring system used for measuring the diagonal lengths of the Vickers indentation is equipped with the required resolution, and here in the case of Vickers, the microscope should have the required resolution, and it has to have the required magnification also for measuring the diagonals of the indentation made by different type of this indenters. I mean, it is one is in the micro Vickers range, other one is in the normal Vickers range. So it should have this kind of resolution, and the maximum permissible error in the resolution is this much. Okay. So methodology preparation, methodology and preliminary object. The hardness testing machine should be checked to it. We have already covered this. The hardness testing machine should be covered and checked to ensure the following before the calibration. The machine is properly set up. The machine is properly set up means we have to check the alignment, and there should be any tilting, because normally whenever we give the specification for the standard hardness block, the flatness, the polished, and the parallelism, the hardness blocks, everything we specify. So the machine has to be set up so that there is no other component which is coming into the measurement and causing error in the system. And the plunger is capable of sliding in the guide without any hindrance. So this is again a very, very important thing. Normally we engage and disengage the plunger in the hardness machine to make the indentation. So there shouldn't be any other frictional component which is coming and hindering the movement of the indenter. So if that is happening, then the applied force will not be same. So we may not be able to make out all those things. We might have calibrated the machine and we might have calibrated it for force, but when you are making the measurement, it is better to check whether the indenter is sliding freely without any frictional force acting on it. Okay, so that is why it is written now. These are the preliminary operation one has to take into account whenever we are making the hardness measurement or hardness calibration, because even that can make a lot of variation in the value. Okay, so that is why the indenter holder with the indenter is firmly mounted. Again, this is another thing, because sometimes we keep changing the indenter. Because for hardness scale, I told you, we have to use diamond indenter sometimes for certain scales, and you have to use ball indenter for certain scales. So the plunger, has the provision to change the indenter always. So whenever you are moving one indenter, when you are mounting another indenter, then it has to be properly fixed. There shouldn't be any loose fitting in the system. Okay. So sometimes even in the Vickers machine we use torret actually, so there shouldn't be any play, or there shouldn't be any other vibration or movement in the plunger. So the plunger has to be rigidly moving without any friction, and there shouldn't be any kind of movement in the indenter. The force applied and is removed without shock and vibration in such a manner that the readings are not influenced. These are all, these things very look simple, but these things can, cause a lot of variation in your measurement. Whenever you apply force, even for load cell calibration also, we always say the force has to be applied without any shock or without any vibration. Then only you can say the applied force is, sort of, purely static force, and if there is any vibration and there is shock, then you will get into a kind of dynamic system. So that is not a desirable thing for making a good measurement. So we have to make sure there shouldn't be any other measurement. Whenever you are having a hardness measurement equipment, you shouldn't be running any other motor or anything like that side in the nearby area. So that will, suppose if a compressor is running in the next room, suddenly it will switch on, and then it can cause some vibration. If there is a vibration and if you are making indentation, then definitely the applied force will vary, and that will also steer your indentation, the geometry, and that will affect your measurement. So you have to make sure there is no other machine, particularly compressor and things like that. If it is running in a nearby, you have to isolate your hardness machine. So that is why the force is applied and removed without shock or vibration in such a manner that the reading is not influenced. So these are the influencing factors. The next is the measurement. The measurement made for the indentation is estimate the surface area of the indentation are not affected by any other external influences. Sometimes the thing is actually whenever you are making measurement on the hardness block, most of the hardness blocks, if you see, just to protect it, they apply oil and keep from for rusting and other things. So we have to make sure this kind of external thing should not influence the dimensional measurement that you are making on the sample after making the indentation. So you have to clean it carefully, and you have to see, I mean, there is no other foreign particle, present on the surface which may influence your the ultimate I mean diagonal measurement, or this diameter measurement that you are making on the sample after the indentation. Then the third thing is, these are all about the machines. Then you have to take care of your environmental condition, whether the environmental condition is conducive for making your measurement, and preparing the data sheet for recording the data, noting down the identification number of the testing machine and reference blocks, hardness test block, hardness value. This is the external requirement. I mean, for seeing whether you are making the measurements without missing out anything. So you can have a proper data sheet on which you can write whether the environmental condition and whether all these factors are addressed well. Then after that you can make the measurement. So measurement procedure, indirect verification of the hardness testing machine shall be carried out at temperature. So this is again, if you are carrying out the indirect verification, then you have to carry out this indirect verification at this within this temperature 23 plus minus 5. And I mean the environmental condition can also influence your hardness measurement, because this force, I mean this load cell, and so it is better to maintain whenever you are calibrating, whenever you are checking the machine. It's better to maintain, because a large window is there, for maintaining the temperature. It is 23 plus minus 5. So in this range you can do the indirect verification of the machine. So the test surface should be clean and it is free from foreign particles. This I have already mentioned, and it's now it's very clearly, I mean, it is also written, your test surface should be highly polished, and both the surfaces are important. Sometimes we don't pay much attention to the supporting surface. The supporting surface in the back surface, the top surface on which you are making the hardness measurement, it is well polished, and it perhaps they apply oil and then maintain it, and it is clean. So when you are making the measurement, you are wiping out that oil, and you are making the measurement on the top surface. At the same time, bottom surface we don't pay much attention, because the bottom surface there can be rusting and other things. So bottom surface is also equally important, because that is a supporting surface. So whenever you make any indentation on the sample, what happens is, when because of the force, sometimes the sample will make a curve actually. So it can bend actually, because it is a very natural thing. If the thickness is not sufficiently maintained, because normally the hardness blocks come from, comes with 6 mm thickness, sometimes 15 mm thickness. Because 6 mm is sometimes good enough, but when you are using a 6 mm hardness block, when you apply force, then it can sometimes curve, so by applying large number of forces. Because of that, your supporting surface will not be proper. So when the supporting surface, it is getting damaged because of the continuous indentation and because of the thickness of the sample. But in some cases, even the supporting surface can develop some flaws or rust, or some foreign particles may be sticking to the supporting, that is the bottom surface. When you are placing the hardness block on the anvil, and when you are engaging the indenter on that, the supporting surface has to be properly in contact with the anvil. Then only the indentation will be proper. Then the measurement that you are making will be more accurate. So these are the things you have to consider, and you have to follow very strictly whenever you are making the measurement. So the test surface and the supporting surface, the top surface and the bottom surface, should be free from any foreign particle, so that your measurement is more reliable. And the third thing is, the standard hardness test block is placed on the flat anvil with the rigid support. I think I am talking about all those things. The rigid support in such a manner that the surface of the test block is normal to the axis. This is what I think I was explaining in a different way. So now the axis has to be normal. If it is, I mean, because the beginning itself, in the last slide we saw that a machine has to be properly, the machine has to be properly checked to ensure the following, that is, the machine has to be properly set up, whether it is properly placed on a hard surface, like the table. Sometimes people even use surface plate, or some hard metal table to place the hardness machine. So it has to be properly placed, and it has to be properly leveled. then only the normal, the surface of the test piece is normal to the axis of the indenter. You have to ensure that, the axis of the indenter and the surface on which you are making the indentation should be normal to each other, right? So these are the precautions and these are the things one has to take care. So I think in this the Rockwell hardness machine, the testing machine shall be verified for each scale. Now, when you are verifying the machine, it is not sufficient to even calibrate the machine for certain forces. You are calibrating the machine for all the forces. If you are using Rockwell A, B, C, then you have to calibrate the machine for the force applied for A and B and C. And similarly, if you are testing the machine, indirectly also for verifying it whether it is performing to the expectation or not, then we have to verify it in all the scales. That is preferable. But sometimes you may not have all the blocks, but in very few cases it is accepted. But the testing machine has to be verified for each scale for which it is normally used. So that is the requirement. Suppose we are using it for the A scale, you get the standard block for the A scale and you verify it whether it is giving the exact reading or whatever is the error, that you should have some way of compensating. For each scale to be verified, reference block from at least two hardness ranges shall be used as a specified in the standard. So now this, again it is all given in the standard 1586. You can refer to the appropriate part, whether it's part 2, part 3. So then you can just follow the procedure for verifying the machine. Then next one is similarly for the Vickers, when verifying the testing machine which is used for several test forces, at least two forces. This is what I was mentioning in the previous one. At least for two forces shall be chosen, with one of them most frequently used. Again, you see the word one of them, whichever, because normally all the scales are not very commonly used. I mentioned that, I am repeatedly saying that all scales are, because you have seen the complete spectrum of scales in the Rockwell, even the Vickers, from 0.01 gram to say 100 kg, and the original 1 kg to 3000 kg. You have seen the spectrum. But normally, if you see, people don't use all the scales. That there are very few scales which are very frequently used. 10 by 3000 is frequently used. 2.5 by 187.5 is frequently used, and HV30, 10, and these are all frequently, HV1, these are all frequently used, and ABC are frequently. So for these scales, basically you have to be very sure. So that's why it is written very clearly. The scale which is more frequently used needs to be checked, and it has to be chosen, and you have to make sure that you are getting the correct reading for that. So the same thing is for the Brinell also. Brinell also, it is the same thing. The testing machine shall be verified for each test force for each size of ball used. So again, here we are using different balls, 1 mm to 10 mm, 1 mm 2.5, 5 mm, 10 mm we are using, and all these balls, you have to check whether the machine is properly functioning or not. And then this is the range. Actually, one is when you are talking about the hand, even in Vickers also, less than 225, because that's a smaller value. The error can be more in this range. Then again, then for 40 to 600 and more than that is more than for 225 HP scale. I mean, this is, you can split it, because the HP scale also varies from from less than 225, it goes up to 1000, 1500 like that. But you don't have to maybe all these, you may not have any material which is having such a value, but commonly you will get 600 HV, 200 HV. So these are really common values. So you can have one in the lower range and one in the higher range. Similarly for the Brinell also, less than 201 and then more than 201 you can take, and the normally available and commonly seen scales are 700 HV per 1000, 10 by 3000 I am talking. So that is the value you normally obtain for any hardness value also. So result, how you can establish the uncertainty and the, basically, whenever you are making the hardness measurement, you have to take 5 measurements. Five measurement means first initially you can avoid two measurements. Then after that you have to take five measurements for the Rockwell scale. And then you can take this E1, E2, E3. I told you in the beginning itself. But E comes by dividing the permanent indentation depth by 2 micron, then you will get the E value. So I told you, I took the example of 50. Suppose if you are getting 50 as the E value, then your hardness is going to be 100 minus E, that is going to be 50 HRA, or if it is the case of HRC, it's going to be 50 HRC. So the E value you have to take, you have to repeat it for 5 times, ignoring maybe initial few readings. That means totally you have to take 7 readings. You can take 7 readings, then you can avoid 5, then 2, then you can take the rest of the 5. And you have to calculate the repeatability. For calculating the repeatability, it is I think the procedure is the same. If you are familiar with calibrating the force equipment, you have to take E maximum minus E minimum, then divided by 5. So that is going to give you the repeatability error of the hardness value. So normally five readings are recommended. This is the same thing with all the other scales also. For Vickers, you are going to measure the diagonal. So it is written D1, D2, D3. So you can take 5 measurements, then you can take the average, and you can calculate the standard uncertainty using these values. Similarly, for the Brinell, again it is the diagonal. So D1, D2 with the arithmetic mean of the diameters of the indentation. So arrange in the increasing order, then you D5 minus D1 will give you the maximum minus minimum by 5. That is going to give you the uncertainty of the sample that you are measuring, and that will give you the standard uncertainty. So now from that value, then again you are going to get the hardness value. Each E or each D will have every E and D will have one hardness value, H1, H2, H3, H4, H5. So you can take the average. So that will give you the average hardness value. Then if you are measuring, if you are having a reference block, then you can just see how much variation is coming from the reference block which is calibrated using a primary standard machine. So that will give you the error in that machine when you are calibrating it for the indirect way. So that you can account for separately. And whenever you are calibrating a machine, then you have to after measuring 5 readings, then you have to check the resolution of the machine. Then you have to check the standard uncertainty that is coming from the repeated measurement. Then you are going to combine this with the standard uncertainty which is given in the block, that is the reference block. Then combining these 3 things, you can give the total overall uncertainty of the machine, and ultimately finally you can include the error in the measurement by seeing the difference between the average value and the reference value. So that is how ultimately it is achieved. So input quantities considered for evaluating the uncertainty of hardness measurement by the testing machine I have already mentioned. So here it is written the repeatability of the testing machine by taking 5 readings, that is the measurement of the reference hardness block which is coming from hardness machine. Resolution of the indicator of the hardness machine. So the hardness machine will have certain resolution, that component will come, or resolution of the hardness machine. And the relative repeatability of the reference block used for the hardness measurement. So this is the relative repeatability of the hardness block. So 5 measurements you are making, so that you can get the standard uncertainty from that. There is a standard way. You are all familiar with that. In fact, the standard uncertainty divided by multiplied by that student's factor and everything you can take, and you will include that as a component in your uncertainty calculation. And the basic measurement capability of the Bernal hardness calibration machine against each reference block U, B, C at K is equal to is finally given by H is equal to HB, that is the average value plus the uncertainty. And if there is an error component, you can add it to the machine. That is a separate thing which is come as uncertainty, is that the error component plus the overall uncertainty. So the majority of the component is, these are the major component. One is the resolution of the machine, and you have to consider the repeated measurement that you are making from your sample. So you will get the standard uncertainty from that, and your resolution and your standard block uncertainty. These 3 components are very critical, and using these 3 components you are going to estimate the overall combined uncertainty. And after the combined uncertainty, for a testing machine, then there will always be a difference, because your standard reference value and the average value that you are getting from the machine is going to be different. So that offset you have to account separately when you are calibrating or when you are checking the machine, and this error component has to be adjusted whenever you are making the measurement. Okay. Okay, I think I have covered. Now I think, yeah, yeah, Ashutosh, any question or any doubt? Because I mean, this is only just to give you an idea, how the hardness
Yes.
standard and various scales are established, and the focus was only on three scales, that is Rockwell, Vickers, and Brunel, and these are the scales mainly used. I mean, what is the standard now. Of course, the ASTM standard is also there, which I have not mentioned. Every Rockwell, Vickers, and Brunel, all these three scales have the corresponding, ASTM scale. The only thing is, in India, we mostly adopt to the ISO standard. So ISO has got 6506, 07, and 08. 6506 for Brunel and 7 for Vickers, 8 for Rockwell, and we have equivalent IS standard. But nowadays there are many people are also using ASTM standard. So ASTM, I don't know the exact number, but I mean, I can get you that actually. So if people use calibrate as per the ASTM standard, but the only thing is, in the ASTM standard, the answer, the requirement is little not that stringent, I would say. I mean, the hardness tolerances. So that is also there now. So ASTM standard, I can get you maybe the numbers exactly if you. I mean, I forgot to mention that one in this. So so based on that standard, I mean, we calibrate the blocks, and the standard machine is established as per that standard, and the testing machine and the general procedure, everything is based on the standard procedure. So it's a kind of process and procedure. It is not a unit. Yeah. With that, I think let me just give the mic to Shastra. Yeah, please. Any question? Any doubt? Yeah, please.
Thank you very much, sir, for your this brief and very informative lecture. Sir, now we are just making all the participants, the panelists, so that they can raise the questions. Now, sir,
Yeah.
if presentation is complete, we can make them the panelist.
Okay.
Your presentation is over, sir?
Yeah, yeah, I think, yeah, it's done actually, because I have covered all the three. It's yeah.
Oh, very good. So now, sir, if you will remove this presentation from this.
Yeah, yeah, sure, sure, okay, sure. If any question comes that I thought, I mean, I may have
Yes,
to
sir.
roll back.
I will request all the participants to kindly switch off their mics and switch on their videos so that we can take your pictures for the social media platforms. And now you are free to ask the questions related with this hardness or something if you wish to ask about the legal metrology, please. Anybody who wish to ask the question related with this hardness topic from the Professor Titus, sir? Dikshit, sir, would you like to speak anything? Would you like to speak or add something?
Uh, this was very nice lecture, and most of the things was covered. And hardness testing is very one of the important things in industry. And uh, you know that lot of the things are wires. Those very strains are being depending upon the hardness testing, because now on these days the so many bridges are also been made uh, through the wire on the cantilever based. So that important has become very uh, useful जो है. Uh, only one of the thing is that जो है that there is a ISO standard and all that very things are there जो है. Sometimes the peoples are asking for the traceability. How to measure the traceability of these very standards जो है. That is a question mark.
Thank you very much, sir. Thank you. Sir, one question is indirect method calibration in Rockwell. Is it required to calculate uncertainty?
Indirect verification means if the machine is calibrated, there are, I mean, two things you can say. One is you are just verifying it, whether it is coming closer to that or not. Otherwise, if you are calibrating the machine using the block, then you have to estimate the uncertainty. Yes, that is what indirect calibration itself, right? Yeah. One is verifying, just checking the machine for its performance. You can use some sample. You can use the standard block. Whether because every day when you are using, the system gets disturbed. And when you are calibrating the machine, then you have to take 5 readings, and you have to take the uncertainty that is arising from these 5 repeated readings, and what is the resolution of the machine, and what is the standard uncertainty given in the standard block. Then you have to take all these components, and you have to arrive at the uncertainty. Then even then there will be a kind of deviation, because the machine per value and the standard block value will not definitely match. Maybe say 0.1 or 0.2. So that will be a kind of bias which you have to add to that fine.
Thank you. Thank you very much, sir. Thank you. Anybody else who wish to ask the question? Sir, my request is you kindly share me this presentation so that I can put it on the website or all the other portals, and the participants can be benefited from it. And we will share this video to all the participants through our portals, Facebook and YouTube channel. They will get this certificates. Last time, few certificates are pending with us, and I hope that within a day or two, we will issue all the certificates at once. Thirdly, I think there was some communication gap. The topic was mentioned torque metrology. I'm sorry, it was hardness today, and there maybe due to this typing error or something, this was made wrongly mentioned. That I'm sorry for that. But next week we have another topic. And if you wish to ask anything, if you wish to add anything, or if you wish to say something, you are most welcome. Please, any of the participant, all of you. Any of the participant who wish to add something? See, from 1st of January, few new provisions under the legal metrology packaged commodities rules are going to come into operation. They will be enforced for in implementation. They will be enforced from 1st of January 2024. Like the very important point is 1st of January, we have to declare the month and year of manufacturing in place of month and year of packing or importing. This packing and importing provision has been omitted. It was omitted in 2021, but it was continued, and regularly we were expanding, considering the problems of the industry. But now it will come into force from 1st of January. This is one point. Secondly, unit sale price, it will also be mandatory from 1st of January. Every commodity has to have declare the unit sale price as per the rules. So few of the provisions are going to change from 1st of January. My request is kindly go through it, and if there is any problem, there is any issue, you can contact me or any of the legal metrology officer, or through our website. All these declarations, all the informations are available on our website. We have another lecture at 2:30 today about the packaged commodities. What are the problems? This is not being basically organized by us. This is being organized by the FSSAI, and 2:30 we have one lecture. I have already shared this link and all in Facebook. If anybody wish to make part or wish to participate in that program, he can do about the legal metrology packaged commodities rules. Few of the rules are going to change from 1st of January 2024, and there should not be anything or any problem with the industry. If there is any problem or the packaging material is pending with you, you can kindly inform us, and you can take the permission wherever required industry wise, that this much problem is, this much packaging material or the products are available which are not there, which you are not able to complete or finish or utilize till 31st of December. Anybody who wish to ask anything or who wish to add something? But these are very important, and these provisions will certainly help the industry as well as the consumer. Unit sale price, and yeah, anybody who is raising the hand, please speak. I'm sorry, your voice is not clear. Anybody who wish to ask, please. About the legal metrology or the hardness metrology, which we have discussed today. Yes. When do we have webinar on talk? Talk was done last time, and very soon we will be having within next 3 months we will be having one seminar on torque. This was the question asked in chat box. Anybody else? Anybody?
Sir, I have a little doubt
Anything
in
which
that.
you wish to?
Hello.
Please,
Sir, this is Mayur Jhade here. I
please.
have a small doubt with regarding to the repeatability of the Brinell testing, Brinell hardness testing. Hello.
Okay.
Sir,
Yeah, please speak.
what would be the criteria for the repeatability of the Brinell testing if I carried out the five indentation and carried out the five testing on the particular material? Then what would be the minimum criteria for the Brinell?
What is the minimum criteria for Britnell?
Yeah, sir. Likewise, you have mentioned that 1% has to be there. In the 1% has to be tolerance in the Brinell. Likewise, is it a kind of a thing related to the repeatability of the five indentation or the five reading?
Yes, actually the tolerance is given no for every that there is a table there actually you can refer to that for the
Okay, sir.
machines, right? So if you are
Okay, sir.
getting five readings, then finally from these five readings you will get the standard uncertainty, right?
Okay, sir.
You will get standard uncertainty. Then I mean you are using your microscope and everything for the measuring the diagonal, right? So
Yes, sir.
that will give the uncertainty due to your measurement, right?
Yes, sir.
Then when you are using a standard block, the standard block itself will have certain uncertainty because that is
Yes,
from
sir.
the certificate. So you can use these three components, okay, for
Yes, sir.
estimating the overall uncertainty in the measurement. But the problem now, what I mean, there may be an issue like your standard block average value and what you are measuring in the machine, there can be a large deviation. So that how much is acceptable that you have to see from the standard table, right? But
Yes, sir.
that is an error component. If it is within the range, then you have to adjust that, right? Basically,
Okay,
you have
sir.
to account for that.
Sir, one more thing. If it is about the part one, if I'm carrying out a hardness testing on a material,
Hmm.
I'm testing a material, then is there a criteria similar to the repeatability if I take the five
No,
readings there?
when you are testing a, okay, now you are talking about a work piece actually. So you have
Yes,
got
sir.
a
Yes,
work
sir.
piece, and then you are measuring the hardness of the work piece, right? So
Exactly, sir.
suppose if the machine is having an error, right? If the machine is having an error, then you have to account for that error. Then
Okay.
when you are making measurement on your workpiece, your question is whether you have to make repeated measurement or one measurement is sufficient.
Yes,
It
sir.
is better to make repeated measurement to make sure that the workpiece is having that much hardness. Because anyway, once you'll be suppose you are not going to make a single piece and you are going to make the measurement and come to a conclusion. So hardness is a destructive measurement, right? So the workpiece what that you are using to estimate the hardness of your product, that is not going to be useful in sometimes because you are damaging it, right, by making indentation on that.
Yes, sir.
Okay, but it is a kind of sampling you are doing and you are making the measurement. Then it is better to make a repeated measurement so that the rest of the samples that you are made, under the same condition, we will have the same hardness value.
Okay, sir. Thank you, sir.
You're welcome.
Thank you. Anybody else? You ask the questions. Please don't hesitate in asking the questions because it is very open platform and you will not get the any expert better than Professor Titus in this subject. So my request is take the benefit of this. Any question, anything which you have in your mind, you please ask about the legal methodology or about this today's discussion. Anybody? Anybody who wish to ask a question? Otherwise, we can close this session for today or the next week. Or if anybody who wish to participate in the packaged commodities rules workshop or seminar today at 2:30, they may participate. It is available on the Facebook. The link is available on the Facebook, on this legal methodology portal as well as in my Facebook. So thank you very much, sir. Thank you,
Okay.
Professor Titus.
Okay,
Thank you all the participants. Thank you, Dikshit sir and NIC team for organizing